Hello, young physicists. Ever wonder why your voice sounds different when you yell underwater or when you knock on a solid door? Here's a fun thought. Why does sound speed change from talking through air to tapping on metal? Hmm, maybe sound likes to travel in style, solid style, that is. So, the speed of sound depends on what it's traveling through, and that depends on some physical traits of the material, things like density, elasticity, and even the temperature. Imagine sound as a runner who's sprinting through different terrains. It zooms fastest through solids, slows down in liquids, and gets really sluggish in gases. Now, how do we put numbers to this? There's a special formula, the speed of sound, which we call V equals the square root of elasticity divided by density. More precisely, V equals the square root of E over the Greek letter rho, where E is the modulus of elasticity, telling us how stiff the material is, and rho is the material's density, how heavy it is per volume. This means materials with high elasticity, like solids, let sound zoom because he is big. But if the density is large, like in some heavy materials, it might slow things down. Gases, on the other hand, have both low elasticity and density, but the low elasticity slows sound more, making it the slowest speed environment. So this beautiful formula shows us that elasticity hypes up the sound speed while density tries to hold it back, like a tug-of-war between stiffness and weight. And there you have it, the medium is not just a background. It's a co-star deciding how fast the sound show plays out. Okay, let's take a quick trip through solids, liquids, and gases, kind of like the three musketeers of matter, and see how sound travels differently in each. First up, solids. Here, molecules are packed like sardines in a can, super close and rigidly held together. This tight packing makes solids highly elastic and almost incompressible. Imagine a crowded elevator where everyone holds hands tightly, any push passes through quickly, which means sound speeds are really high. Moving to liquids, the molecules are still close but looser than in solids, like a less packed crowd at a concert. This means elasticity drops, and so does the speed of sound. But it's still faster than in gases because the molecules are closer than in air. And speaking of gases, the molecules are like teenagers at a mall, spread far apart and bouncing off each other weakly. This makes gases highly compressible and less elastic. The bulk modulus here is quite low, so sound travels the slowest. Just to pin some numbers on this, in steel, a classic solid, sound races at about 5,000 meters per second. In water, it's more like 1500 meters per second, and in air at 20 degrees Celsius, a comfortable room temperature, it's about 343 meters per second. So next time you knock on a metal door or talk underwater, remember, molecular closeness and stiffness are the real reason why sound changes speed. Ready for a little history mixed with physics? Let's talk about Newton and Laplace, not the apple falling Newton, but the sound speed Newton. Sir Isaac Newton first tried to predict sound speed in gases. He thought, hey, sound travels at the square root of pressure over density, or mathematically, V equals the square root of P over rho. However, his formula underestimated the real speed because he assumed the gas temperature stayed constant while sound passed, an isothermal process. But sound moves fast, so that assumption didn't quite cut it. Then came Laplace, who said, hold on, Newton. The gas doesn't have time to exchange heat. It compresses and expands almost instantly, making the process adiabatic, not isothermal. Laplace introduced gamma, which we call the ratio of specific heats, symbolized by the Greek letter gamma. This changes the formula to V equals the square root of gamma times P over rho. For air, gamma is about 1.4, That's just a fancy number telling us how heat capacities relate. When we plug it in, the formula matches what we actually measure in experiments, like magic. The key insight? Sound waves move so rapidly they cause pressure and volume changes without heat transfer. That's why the adiabatic correction is crucial. In simple terms, your voice creates tiny, lightning-fast compressions and stretches in air. Hot and cold changes don't happen during the wave, making sound a very clever traveler. Now, here's a fun fact that'll make you sound like a science wizard at your next party. Sound doesn't just depend on where it is but on how warm it is. In gases, as temperature rises, molecules move faster and bump into each other more energetically. Think of it like a dance floor. Hotter means dancers are stepping quicker and sound travels through this energetic crowd faster. The relationship comes from kinetic theory, where the speed v equals the square root of gamma times r times T over m. Don't worry, that's just fancy physics speak where T is absolute temperature in Kelvin, m is molar mass, and r is the universal gas constant. So what does this practically mean? For a fixed gas, sound speed goes up with the square root of temperature, written like V proportional to the square root of T. So on a sizzling summer day, your voice might carry just a tiny bit faster than on a chilly winter morning. This temperature effect is even important in real life. Pilots and engineers consider it when timing sonic booms or designing instruments that rely on sound waves. So heat your physics brains, literally. Let's dive into liquids now, pun intended. How does sound move through water or juice? Easier than you think. Once you know they have their own special elasticity measure called the bulk modulus, symbolized by B. The speed of sound in a liquid equals the square root of B over rho. Here, bulk modulus tells us how hard it is to compress the liquid. The tougher it is to squeeze, the faster sound zips through. For example, water has a moderate bulk modulus and a relatively low density compared to metals. When you plug in the numbers, sound travels in water at about 1500 meters per second, 4 to 5 times faster than in air. And here's a salty twist. Sound travels faster in salt water. The dissolved salts increase density and affect compressibility, tweaking bulk modulus and letting sound speed up. It's like sound wears sneakers in salt water and boots in fresh water, boots being heavier and slower. So whether it's underwater sonar or a dolphin's chatter, liquid's bulk modulus is the secret behind how sound races through waves beneath the surface. Now solids get a bit more complicated but exciting. Did you know solids can carry not only longitudinal waves, the push and pull sound you're used to, but also transverse waves, a side-to-side shake? The speed of longitudinal waves depends on Young's modulus, Y, which measures lengthwise stiffness, while transverse waves depend on shear modulus, G, which measures resistance to twisting or shearing. Formally, the longitudinal wave speed equals the square root of y over density, and the transverse wave speed equals the square root of g over density. Since Young's modulus is generally higher than shear modulus, longitudinal waves usually travel faster. Think of it like running down a hallway, longitudinal, versus trying to shimmy sideways through a crowded room, transverse, lengthwise is quicker. Steel, for example, has highly bonded atoms and gigantic elastic constants, pushing sound speeds in solids from 5,000 up to 6,000 meters per second. So solids are like VIP highways for sound, fast, multi-lane routes carrying different wave types at super speeds. Alright, time for some number crunching. Don't worry, I'll walk you through it. Imagine a steel rod. Given Young's modulus Y is 2 times 10 to the 11th pascals, yes, that's 200 billion. And density rho is 7,850 kilograms per cubic meter. We want to find the speed of sound, V, in the longitudinal mode. The formula, as you recall, is V equals the square root of Y divided by rho. So, plugging in, V equals square root of open bracket 2 times 10 to the 11th close bracket divided by 7850. Calculating inside first, 2 times 10 to the 11th divided by 7850 gives approximately 25,480,000. Then V equals the square root of 25,480,000, which is about 5048 meters per second. This matches well with known speeds of sound in metallic solids. So, no surprises here, physics delivering accurate results as always. See? Even large numbers obey these neat rules, and you've just solved a real-world problem. Let's wrap it all up. Here's the cheat sheet for sound speed across different media. First, the general formula, speed of sound equals the square root of elasticity over density. That's your basic rule for any elastic medium. For gases, remember Newton's initial formula underestimated things. The corrected, true formula by Newton and Laplace includes gamma, the ratio of specific heats. Speed equals the square root of gamma times pressure over density. In liquids, the speed depends on bulk modulus and density. Speed equals square root of bulk modulus over density. And in gases, speed increases with temperature, following the square root of absolute temperature relationship. Overall, sound moves fastest in solids, then liquids, and slowest in gases. Why? Because solids pack molecules tightly and are very elastic, while gases are loose and compressible. Also, solids support two wave types, longitudinal and transverse, with different speeds depending on their elastic moduli. Key players controlling sound speed are compressibility, density, and the specific heat ratio gamma in gases. Finally, sound waves cause adiabatic changes, not isothermal ones, so don't forget that correction. It's vital for matching theory with reality. That's it for today's sonic journey. Remember, physics is as much about vibrations as it is about curiosity. Keep your ears open and your brains buzzing. See you next time for more exciting explorations in sound.